and welcome to the second lecture in this series. So on the first lecture on Monday, we had a bit of an introduction about ore deposits, their history, and how they're used, the mining process, the type of ore deposits, and a bit on the environmental consequences of mining and extraction. Today we will be looking in a bit more detail at magmatic ore deposits. And this is a picture from a layered intrusion. Obviously we had sequence crystallization of some felsic accumulates, followed by sudden crystallization of layers of chromite. And this is a picture of KOMATITE lava. Are you familiar with what a KOMATITE is? Better there? Oh, we will come to that. So during this lecture we will be looking at what magmatic ore deposits are and processes that are needed to generate them, and then we will look in a bit more detail on a few examples. So magmatic ore deposits are those deposits formed directly from a magma through a variety of processes such as saturation caused by magma mixing or assimilation or fractional crystallization. And because of their nature, then these deposits occur within or at the boundary of igneous bodies, whether these are intrusive or extrusive, it doesn't matter. And they are sources of these metals. Do you know what PGE is? PGE? Platinum group elements. So platinum, palladium, and so on. Incidentally, this Elements magazine that treats in a bit of detail PGE deposits and their occurrence and associated topics. And we will not be looking at deposits that are associated with aqueous fluids released by late crystallizing magma. This will be the topic of the next lecture. So magmatic ore deposits often occur as massive sulfides or oxides, which is what is precipitating. This is a case of copper-nickel mineralization, as you can see from the scale. The geologist here, it's about a meter or a meter and a half thick layer of sulfides, which is pretty good. And this is even better. This is a core section through, well, a massive sulfide deposit, and it goes for several meters. So you can imagine that exploration companies, mining companies are very happy to find stuff like this. Or alternatively, sulfides or oxides can occur as disseminated ores. And this section through the lava flow with the golden blebs being sulfides. Here is just an enlargement of that. So basically the sulfides occurring in between silicate minerals, in this case olivine, serpentinized olivines. And here on the corner is just a three-dimensional view of what this would be, with the blue being the sulfide blebs, and the spaces in between were basically silicate minerals. This was created using microcomputed tomography, micro-CT, where the sulfides have a density that is different from that of silicates, and so will give a different response, and hence can generate reconstructions like that. Depending on the host magma, we will have different deposit types in more mafic magmas, we tend to have metal deposit of nickel, cobalt, chrome, copper, and PGEs, whereas in felsic magmas we have different metal association: lithium, tin, tungsten, uranium. And because different magma types occur in different tectonic settings, deposits also tend to be associated with different tectonic settings. So, as you know, basalts are very common, mid-ocean ridges. All the ocean floors are made of basalt. But they also sometimes occur in interplate settings, such as in the Oakland volcanic field. Well, the Oakland volcanic field is not really related to any ore deposits, but if we had larger intrusions, then we would possibly form layered intrusions which can crystallize and form ore deposits. And in the past, again, this term, komatites, which do not occur today, they do not occur today, they occur mostly in the Archean, and we will come to that in a few slides. Granites instead tend to be associated with arcs and orogenic settings. So, as I mentioned, and as you know, not all lavas contain ore deposits. So, ore or metals need to be enriched in the magma in order to have something that is economically viable. And this can occur by a variety of processes. And here we start by looking at where the magma comes from. And the magma comes from partial melting of the mantle, for instance, or the crust. And during partial melting, we have different behavior of different chemical elements. So this equation for batch melting, and you don't need to worry about knowing that equation by heart or anyway. But it would be good if you would become familiar with the effect of changing parameters in the results. And so on the horizontal axis, we've got F, which is the melt fraction. So 0 would be a solid peridotite, and 1 would be basically the molten peridotite. C is the concentration of a certain element. C liquid is the concentration of the element in the magma, and C naught, C0 is the concentration of the element in the peridotite. And D is the partition or distribution coefficient, can be called either ways. Do you all know what a distribution coefficient is? Yes? So I don't need to go into too much detail, but just to explain these curves, if the distribution coefficient is very small, it means that the particular element does not like to remain in the solid phase. So as soon as we start melting, this basically goes into the melt. And that's why for low degrees of melting, the concentration in the liquid would be very high. At the other end, if an element likes to remain in the solids, such as nickel in olivine, melting will not cause that element to enter the magma. The element will remain in the crystal, and so we won't have much of it in melt at low degrees of melting, but as we increase the degree of melting and we melt more of the peridotite, the concentration will increase. Another way of looking at it is on this graph, which links to this image here. Here we have, again, percentage melting of peridotite, which would be basically F. And here we've got the concentration of selected elements. And you can see from these curves that platinum and palladium, for instance, they are PGEs. They like to remain in sulfides. So this is the beginning, no melting. We start melting, the sulfides do not melt straight away. So the first phases of melt pyroxenes, clinopyroxene, orthopyroxene. And hence there won't be many of these PGEs in the initial melt. But at some stage, around 11 to 12% melting, the sulfides basically go into the liquid all at once. And so we have this sudden enrichment in platinum and palladium. But then we've gotten rid of all the sulfides, so the more we melt, the more we dilute this signature, and hence we decrease here the concentration of PGEs in the melt. On the other hand, for nickel, nickel likes to reside in the residual silicates, and we need to melt more and more of them to increase the concentration of nickel in the magma. Can everyone follow me? Yes? Last one, please. No? We'll come back to it. I also mentioned fractional crystallization or saturation due to mixing or assimilation. And this is basically the same plot as what we saw before, but reverse. So F again is the melt fraction, but here now we have got a magma. So we start with 100% melt, so we start from here. If the distribution coefficient or the partition coefficient of an element is less than 1, it means that that element does not like to enter whatever crystals are crystallizing, and hence the more we crystallize, the more we concentrate that element in the residual melt, until that element becomes saturated and we start to crystallize it. And in picture, so we've got the magma that's from the mantle is injected in the crust, forms magma chambers or magma reservoirs, and then we start to crystallize after we reach saturation. Another way of reaching saturation is, for instance, by mixing sulfur in with the magma. If the magma is rising and intersecting some sulfur-rich sediments, for instance, the magma is hot. It can entrain parts of these sediments and assimilate the sulfur, which enriches the magma in sulfur and might cause saturation of certain selected sulfides, and so we end up with precipitation of sulfides. So now we look at for deposits in layered intrusions. And layered intrusions are basically, as I said, magma injected in the crust in a magma chamber, and due to decreasing temperature, it starts to crystallize, and different mineral phases crystallize at different temperature at different times. So we form the layers of initially mafic minerals, olivines, followed by pyroxenes and larger phases, and so we end up with kind of layered bodies, as you can see here. This is in the Isle of Ran in Scotland. This particular layered intrusion is not associated to particular mineral deposits, but up at the top there are named a few. The Bushveld complex in South Africa is a famous one. Great Dyke, not as famous. The Stillwater complex in Montana, and the Skaergaard intrusion in Greenland. And these are usually sources of chrome, copper, and PGEs. And this is a section through the Bushveld complex with, as you can see, lower zones composed of Harzbergite and orthopyroxides, or mafic-rich cumulates. Then we have layers of chromides, famous Merensky reef, which is an enriched, thick chromite and sulfide-rich layer. Then we go further up where we start to have more evolved cumulates, some magnetite layers, ending with diorite and graphite, which are very evolved quartz feldspar residual melts. So, how to explain those layers that occur in layer intrusions? I mean, the 4 layers, the massive oxides and massive sulfide layers. So this is a ternary diagram. We've got olivine, chromite, and quartz on the 3 corners, and the enlargement here is from this false lever near the olivine corner. And for instance, let's say we start with a magma with composition of plots near A. It's in the olivine field. We start crystallizing olivine. So the magma moves away from the olivine corner until it hits the protectic, which is a point where both olivine and chromite starts to crystallize. And so temperature will continue to decrease and magma will continue to crystallize. The composition will move along the protectic up to point C, where then we start to also crystallize both the pyroxene. But here we've got basically silicate and oxide crystallizing together, so they will just settle together because they're denser than the melt. And so we would end up with disseminated oxides or sulfides. So simple crystal fractionation and crystallization does not explain the presence of these massive sulfide ore deposits. So other processes have been proposed. And that at the top is the same ternary phase diagram. Again, we start with a magma with that composition, crystallizing olivine, and hits the protectic again, starts crystallizing both olivine and chromite, and it keeps going up to D, where crystallizing orthopyroxene. And at that stage, we inject a new magma batch inside this evolving magma chamber with, say, composition an E. So these 2 magmas, D and E, will interact and mix. And mixing them forms composition F, which is entirely in the chromite field. And so we will have basically saturation of chromite on once and crystallization and precipitation of chromite alone without silicates. And hence we form these massive chromite or chromitite layers. Another way of looking at it on the sulfide solubility curve, we start, we've got crystallization, percentage of crystallization on the x-axis, and we've got weight percent sulfide on the y-axis. We start with a magma that has 0.3 weight percent sulfide, which is below the solubility curve, and so we just crystallize olivine. Crystallizing only olivine leaves the sulfide dissolved in the melt and concentrates them, so it enriches the melting sulfide up to the point where the concentration of sulfide hits the solubility curve. So we start to crystallize sulfides as well, together with all the pyroxenes, and then later plagioclase plus all the pyroxene. And again, let's say when we reach the lower temperature point D, we inject a new magma batch with the same composition there. These 2 mix, and we have mixed composition at AD, which is over the sulfide solubility curve, and therefore we have basically sulfide saturation and precipitation, and we form these massive sulfide layers. Everyone clear? So, looking at the dynamics of magma mixing, and this can be dependent on the density of the original melt, the evolved melt, and the new injected melt. So if we look at this graph, temperature, density, we start with a new magma with a density of about 2.58. We remove olivine from its olivine is denser than that magma, and so removing something dense from a magma will reduce the density of the residual melt up to the point where we start to crystallize orthopyroxene and later plagioclase. Orthopyroxene and plagioclase are lower density phases. So we remove something that has relatively low density from the melt. We basically make the melt more dense. And therefore, the evolution of the melt density goes back up. And after a while, you might end up with a melt that is more dense than its parent. And then, if we mix, or if we inject a new fresh magma, let's say we inject a new fresh magma early in the crystallization history, when, for instance, we inject it at this point, the new magma has this density, the residual melt in the magma chamber has this density. So the new magma has higher density. And so we inject it, and because it has higher density, it goes up a bit and then flows along the floor to form this fountaining. On the other hand, if we inject a new magma late in the history of crystallization, where, let's say, the magma chamber has reached this point, basically the new magma has a density which is lower than what it is including into. And because it's lower density, it will float. And so we have these plume-like mixing. And because of turbulence, this is more efficient for mixing, and also where it mixes, basically the sulfides, which become saturated, can precipitate directly onto the base or the bottom of the floor of the magma chamber and form these massive sulfides. As opposed to here, where we might have some mixing, but this is not as efficient, and also we would have crystallization also within this magma, and we might form disseminated sulfides. So to summarize, igneous layer intrusions. We have the magma injection in the crust, starting to crystallize silicate phases of the orthopyroxene. And then at some stage, we inject a new melt early in the history of crystallization. We form this fountain behavior of mixing, because we are forming it relatively early in the history of crystallization. There isn't that strong saturation of oxides, and so we form not that rich disseminated deposits. On the other hand, if we inject a new magma later in the history, we get A, better mixing dynamics, and B, also greater oversaturation of the oxides, and so we can form this economically viable, interesting massive sulfides and massive oxide deposits, as you can see in these images. That's the famous Merensky reef. These are basically extensive, and they go for 250 kilometers. Chromitite layers. Chromitite is a rock which consists mostly of chromite. Another example, this is also from the Bushveld complex, where we have some kind of an orthosite, then a layer of chromitite, and then some disseminated sulfides, with what looks to be some feldspar as well. This is from the Stillwater complex, where we have subplatinized danite in black and interstitial platinum group elements rich pyrite and chalcopyrite. And this is an example from Western Australia, where you can basically see all the layers with gabbros and glucogabbros, and layers of magnetite, which is rich in vanadium and titanium. That in mind. So, how do you turn a $300 car into a $10,000 car? You park it in the right place so that it gets hit by a meteorite. You probably wonder, well, so much. What's the point I want to make here? Well, just with a bit of a larger scale. Well, this is the meteor crater in Arizona, and this is the Sudbury complex in Canada. And you can see the scale here, 10 kilometers, so it's 50 kilometers across. So whatever formed that must have been a bit bigger than the rock that hit that car at the beginning. And because of the heat generated during the impact, the crust was molten. And that was sulfide-rich basalt crust. It basically formed magma ocean or lake, given the dimensions. And within this basaltic magma lake, we have convection and sulfides that basically gather and precipitate towards the bottom, towards near the breccia, so the broken up rock caused by the impact. And basically this formation of massive sulfide deposits, and therefore that's how you go from a relatively not so valuable pile of basaltic lavas to a slightly more valuable pile of massive sulfides. In this case, chalcopyrite, pyrite, and pentlandite. We will see pyrite and chalcopyrite and pyrrhotite next week during the lab. We won't be seeing pentlandite, unfortunately, because we don't have it in the collection. Moving on to komatiites, hosted sulfides. So komatiites were basically lavas, lava flows. So not all were flows. But they are extremely high temperature, so 1600 degrees and low viscosity, so they flowed and formed probably very broad shields, somehow like Hawaii might be these days, nowadays. And they occurred, as I mentioned, mostly in the Archean. So there is an occurrence of komatiite in South America that is 90 million years old, but none is known to occur today. And why they occurred mainly in the Archean is because during the time the mantle was, or the Earth was hotter, the mantle was hotter, and when it melted, it could melt to a greater degree. And if you remember that plot at the beginning, in order to enrich certain elements, we have to melt more and more of the peridotite. So nickel, for instance, and nickel deposits occur in komatiites. So komatiites were about 40 to 50% melting of the mantle peridotite. So we have a relative enrichment of nickel. But not all komatiites contain ore deposits. So most komatiites are sulfide undersaturated. So we need to find a way of enriching the komatiite lava with sulfur so that we can precipitate the pentlandite. Oh. And not all komatiites were lavas, some were just intruded. So sources of extra sulfur, as I said, you could have sulfide-rich or sulfur-rich deposits, like sulfidic shales, or volcanogenic massive sulfides, BHMS or VMS, which we'll be looking at in lecture 4, I think. So, as we mentioned, the komatiite were very hot lavas, so 1600 degrees. It's not enough to basically melt the substrate of the lava flow, or melt and incorporate things, intrusions of komatites going into. And these eroded flow, or what the lavas or magmas are intruding, are sulfur rich. The sulfur becomes incorporated within the komatite melt, increases the sulfur content of the melt, which allows saturation and deposition of nickel sulfides that can form either as massive layers or disseminated layers or disseminated patches. So just a summary diagram. We start with the komatite, which is 100% melt. We either incorporate some sulfur-rich country rock or floor, or else another way is by assimilating silica-rich or felsic country rock. And looking at this diagram again, very useful. If we have a magma at this point and we mix it with a silica-rich country rock, we basically end up with a composition which is all within the chromite or the oxide or sulfide field, and so we have sudden saturation of sulfides. And nickel, a chalcophile element, likes to bond with sulfur, so we have this precipitation of sulfides, and then depending on the dynamic of where this process is occurring, we'll have either settling, if there isn't any current, and we form massive ore, or if it's in a lava flow, let's say, these particles do not settle, and we might end up with disseminated ores. And if you're interested in that, you can go and explore KAMBALDA, which is a beautiful place in Western Australia, where people are so desperate that they are mining through the Salt Lake. And on weekends, they go and play golf at the local golf course, where the greens are just a darker shade of the brown than the surrounding countryside. Just a place.